Hello, my awesome Algebra 2 students. Today, since I can't be with you, you get to listen to my voice. Would you please open your books to page 60? Today we're looking at lesson 10, talking about situations and sequence types. So on the top of page 60, we've got a list of numbers in a sequence, and it says that it's a geometric sequence. I want to know what the growth factor is. Usually we call the number that we've been using a growth rate. A growth factor is a little bit different. I want to know on this one, what do I have to multiply the 16 times to get to 24, or the 24 by to get to 36? Some of you can maybe do that in your head. If that's not an easy one to see sometimes, what we want to do is take the second term, for instance, and put it over the term right before it, the first term in this case. I just picked those two numbers. You can choose any two numbers that are right next to each other in the sequence, but we always want to put the newer number, the next step in here. So I've got step 2 over step 1. New number goes over the original one. If I would simplify this, 24 over 16, I could divide both of those by 8. And now I get 3 over 2. My growth factor then, as a decimal number, as a fraction, is 3 over 2, or we could call that 1.5. Okay. The reason I wanted the decimal there is to help us out with number 2. It says one way to describe the growth is to say that it's growing by a certain percent each time. And we need to know what number goes in the blank for that. So it was the original number. So for instance, if I started with that 16, then I added 8 to that, which is half, or 8, not 5, half of the number that we started with. So that's actually growing by 50%. And if you would continue that pattern, if you would take 24, half of that is 12, add it on, and we get 36. And keep going with that pattern. But this is increasing by 50% each time. So some other things that I want you to know here, again, the growth rate would be just R, which is 0.5 as the decimal, or 1/2. It's increasing by that 1/2, but usually we are looking at what the actual growth factor is, like what I actually multiply by to get from one term to the next. I think I might have switched those around before, but growth factor is what we have been using. For this, I can also do some work, like I could find the nth term in the sequence if I wanted to, as a non-recursive definition. So for the nth term, for any term in the sequence, I'm going to say that, I'll use a G for this one because we know it's geometric. G of any number, G of n, is going to be the first term that I've got there, 16, times 1.5, or 3 over 2, to the n power, if n is greater than or equal to 0. Okay. Still on page 60, we've got these population patterns for 2 different animals. It doesn't tell me what these animals are, but I want to know for each population if it's arithmetic or if it's geometric. So looking at this, I'm hoping that you can see that population A has to be arithmetic. And that common difference, the number that we're adding every single time, is 6,000. Population B, I'm certainly not adding the same amount every time. But if you do that same trick that I was just talking about with the last one, if I would take these two numbers right here, remember the new number goes over the original number, 3750 divided by 3125 is going to give us 1.2 as our growth factor. So the growth factor for this one is going to be 1.2 for that. Okay, So it says write an equation to define population A and write an equation to define population B are the two things that we're doing right here. I want to be able to write this both ways, recursively and with the nth term. So if we are looking at this for the recursive way of writing this, we're going to have, because we have year zero, year since 1990, so that would be at the starting amount, we're going to use our year zero in there. It's going to help us out with this. So I would say A of 0 equals 23,000. And then I would have A of n equals the term before it, so A of n minus 1 plus 6,000. And since we started with year 0, then it's always the next one after that. So this is going to be n is greater than or equal to 1. The nth term, or the explicit term that we call that sometimes, let me use a different color here so it's easier to see. The nth term, again, we've got year 0, so we would use the recursive form, the non-recursive form using 0 in there. So I would say for this one that it's going to be, excuse me, A of n equals, and just looking at our form that we've got there, I want to have the starting amount, which is A of 0, so 23,000. And we're going to add on 6,000 every single year. And this is starting at year 0, so this would be for n is greater than or equal to 0 on that one. So we can start right at year 0 for that. Oh, sorry. All right, for number 3, it says, let's do that same thing for population B, right? And again, we've got year 0 in there, so we're going to have a geometric sequence for this one. But let's write the recursive form. I would start this one, because this is population B, we're going to say B of 0. This one starts at 3125. And I would say for any term in the sequence, I'm going to take the term before it and multiply by 1.2, right? And then we've talked about you can put the 1.2 in front or behind. I'll write it in front on this one. Okay, so we would take the term before, multiply by 1.2, and this is for n is greater than or equal to 1. Okay. The nth term for this would be B of n equals, and again, our form just says whatever our starting amount is, which is B of 0, we know that number, which would be that 3125. And we're going to multiply that by our growth factor, which is 1.2 in this case, and the exponent on that is n. So it's just how many times do we have to multiply it by 1.2. And again, this one is going to be for n is greater than or equal to 0. The question at the end of this says, will population B ever overtake population A? Well, clearly it's starting a lot smaller. They're both growing, but because B is geometric, because it's multiplying, it's exponential, it is absolutely going to overtake population A. We could get this by graphing those two, but I'll tell you that that happens between year 21 and 22. So between the year 2011 and 2012 is when that happened. But does population B ever overtake population A? Yes. Exponential patterns always grow faster eventually, even if it's only got a 20% growth rate. Okay, on the top of page 61, we've got this pattern. Notice that starting with step 1, not step 0. I want to know the sequence W, so the W of n is the number of white squares in any step, and I want to define the sequence for B, which would be all of the black squares in any step. Okay, so let's just start by getting some numbers here. Let's figure out how many there are in each one of these. The white squares in this one, I've got 4, 8, 10. And the black squares, I know that it doesn't really look like actual squares there. I've got 2 black squares. In step 2, I have for white squares, we've got 1, 2, 3, 4, 5, 10, 14. And black squares, again, if you want to draw that in to help you to see it, that's fine. But I've got 6 for black squares. And for step 3, my white squares, 1, 2, 3, 4, 5, 6, 12. I've got 18. And black squares, we really have a 3 by 4 grid in there, so there's 12 black squares. All right, so let's look for some patterns here because I need to know if each of the sequences is arithmetic, geometric, or neither. The white squares for this went from 10 to 14 to 18. It's clearly just adding 4 every single time. So the white function is going to be arithmetic. And my rate of change is 4. For the black squares, went from 2 to 6 to 12. So I'm clearly not adding the same thing every time. And to go from 2 to 6, I'd multiply by 3, but 6 times 3 is not 12, so it's not geometric. So this one's going to be neither. We will have to figure out what that pattern is for number 3 in just a minute. But again, because it doesn't have a rate of change, because it doesn't have a constant growth factor, it's not going to fit either one of those 2 patterns. So for number 2 now, it says write an equation for sequence W. Again, I'm going to do both recursive and nth term. So for the recursive, when I'm writing it like this, I have step 1. So let's just use what we've been doing in the past for step 1, right? I would have W of 1 is 10. So we started with 10 in the first step. And W of any step number would be the one before it. And we were adding 4. And because this started with step 1, we're going to say for n is greater than or equal to 2. The nth term for this, I would do this one. Now, I don't have step 0. However, I could figure out what would be in step 0. And in fact, I really like to write my nth terms in terms of 0, in terms of step 0. So if I have step 0 over here, I don't even need to draw a picture. I know that it was increasing by 4 every time, so if I back up a step, the white squares would be 6. So that's my starting number. So for my nth term, for my definition, I would have any term in my sequence is going to be, and again, just looking at the way that we write these, because this is arithmetic, I need to know what my 0 step is, which is 6, plus, and then I would put in whatever I had for my, my growth factor. I would have this as 4 times the step number, right? 4 is my rate of change, or my common difference, times the step number. And because I started this one with step 0, I would have to say for n is greater than or equal to 1. Right? We don't really have a step 0, so I would have to start this one at 1. And if you're not sure if it's done right, you can always check that nth term, right? If I look at step 1, there are 10 white squares. If I put a 1 right here for the n, for the step number, 4 times 1 is 4, plus 6, yep, that's 10. If I would put a 2 in there for step 2, 4 times 2 is 8, plus 6 is 14. That's how many squares we have there. So you can check it by substituting in. All right, sequence B. Again, it's not arithmetic, it's not geometric, so this one is not as comfortable for us because we don't just have a basic setup for this. But for the recursive form for this one, I would say for this one, in step 1, I had 2 black squares. And to get to any term in my sequence, now this is where I need to know what is happening here. We didn't have a constant growth rate. We didn't have a rate of change. So I need to figure out what's going on. If you look at the diagram, I started here with a 1 by 2 rectangle. And then it's a 2 by 3 rectangle. And then it's a 3 by 4 rectangle. So we can see kind of what that pattern is. I also want you to notice that step 1, like the height of it is 1, and the width is 1 more than that, it's 2. Step 2, the height of that black square in the middle of that black rectangle is 2, and I've got 3 for the length on that. It's 1 more than that. Step 3 has a height of 3, and this width is 1 more than that, it's 4. So the way that we're going to write that is, for my recursive one, we're going to say the step number, we've got b of n equals, I'm going to have, I actually want to do the recursive one first because that's what I was just talking about, or the non-recursive. Let's do the nth term first because that's what I was just discussing. So this would be b of n is going to be whatever the step number is times 1 more than that for the width, because it was always 1 more than what we had, for n is greater than or equal to 1. Right, so in step 1, I would have 1 times 2 black squares. In step 2, I would have 2 times 3, 6 black squares. In step 3, I've got 3 times 4, 12 black squares. So that fits that pattern for that nth term. For the recursive one, if I can go back to that now, I would have to take whatever I had in the step before and figure out what's being added every single time. So this, I think, is harder. To go from step 1 to step 2, I added 4. To go from step 2 to step 3, I added 6. Right? When I added 4 here, that's really step 2 times 2. When I added 6, that's really step 3 times 2. So I'm adding 2 times the step number. Again, I think that the recursive one in this case is much more difficult than the nth term. And this would be for n is greater than or equal to 2 because we started at step 1. Number 4 says, is the number of black squares ever larger than the number of white squares? Well, in these 3 pictures, it's not. But again, this is a multiplication. I know it's not exactly exponential, but I've got n times n plus 1. It's going to be growing pretty quickly. It's not growing at just a constant rate like my white squares were for the arithmetic sequence. So yes, it's absolutely going to. If we would draw out step 4, in fact, that's where it would get bigger. And then every step after that, there's more black squares than white squares. Okay. I'm guessing that some of you have heard of the Fibonacci sequence, and it's just kind of a cool sequence that I really like. But it says the definition for the nth term of the Fibonacci sequence is surprisingly complicated, and this does look absolutely complicated. The Fibonacci sequence is just taking numbers in a sequence and adding. I can show you what this is. It'd be 1, and then 1, 2, 3, 5, 8. It's adding, like these 2 numbers get added together to give me this one. And then I would add 2 plus 3 to get 5. And then 3 plus 5 gives me 8. And then 13, right? So you can keep going with that sequence. It's not hard recursively to find it. But if you wanted to go very far into the sequence, you have to go through all of the steps. So there's an Italian mathematician that figured out what this actually is as the recursive form, and pretty messy, right? So number 1 says, for which form, recursive or nth term, is more convenient to use for finding f of 5? Well, I guess f of 5 wouldn't be that difficult to do with the recursive form, because, I mean, you can just list them out for that one. Even for f of 10, finding the 10th term in the sequence, not that hard with the recursive form. However, when we get to something like this, the 100th term, most people don't want to write out 100 numbers to get to that term. So even though this is kind of messy, probably for this one, we would want to use the nth term, right? For just a couple of numbers, the recursive one is fine. The nth term is going to be a lot easier when we get to big numbers. And then number 2 says, what are some advantages and disadvantages of each form? Well, for the recursive, you just have to go through all of the numbers to get to where you want to be. For the nth term, it's messy and complicated. And if you're putting this into your calculator, if you don't put it in just perfectly, you're going to make mistakes, right? There are so many places to make mistakes in this. So it totally depends on which one you're going to be using based on how far you need to go into the sequence, I think. The disadvantage, again, of the nth term is just how messy and complicated and full of errors it could be if you're not careful. The advantage is you can just jump to, if you wanted the 100th term or the 1000th term, you can put that number in for the n and just crunch those numbers. Okay. Situations and sequences is what we were talking about today. Is one representation easier to use than another? I do think that a lot of times the nth term is easier than the recursive term in some cases. It depends on which one you are more comfortable with. There is not just one right answer for this, so you can choose whichever way you like to do this. Today's homework is on page 63 and 64. I would like you to do all of those problems 1 through 7. If you have any questions, feel free to send me an email.